Hello everyone, this is Hussein Termos, and this is a revision session for Quiz 1 in Math 218, organized by the Cultural Club of the South. Let's jump right into the problems. In problem 1, we are asked to find the values of k for which the following system has a unique solution, no solution, and infinitely many solutions. For these problems, we start off by writing the augmented matrix of the system. And then we use row operations to get it to row echelon form. My thought process here is I want to make these two entries equal to 0 by adding a multiple of row 1 to them. This entry is already 0, so I'm not going to worry about it. For this entry, I'll just add row 1 as is. So 1 times row 1 plus row 2. I'm going to add row 1 to row 2. So 1, 2 minus k, 0. Now if I add row 1 to row 2, I would have 0, 5, k squared minus k, and k, and then 0, minus 5, minus 2, 1. Now I want to make this entry 0, so I'm going to add row 2 to row 3. So I have 1, 2, minus k, 0, 0, 5, k squared minus k, k, and then 0, 0, k squared minus k, minus 2, and 1 plus k. So this is the row echelon form of the augmented matrix. Now for part A, we want to see what values of k guarantee that the system has a unique solution, and usually we focus on the last row to answer such questions.
So in this case, to guarantee that we have a unique solution,
we have to guarantee that this value is not equal to 0. Because if the coefficient of z is some non-zero value, then I have 5z equal to some constant depending on what the value of k is, then z is equal to c over 5. So I can solve for z, and then I can go upwards and solve for y and x eventually. But if this was equal to 0, then I would have 0 equal to c, and then I would either have no solutions if c is non-zero, or infinitely many solutions if c is 0. So to guarantee that I have a unique solution, I want the coefficient of z to be not equal to 0. So k squared minus k minus 2 not equal to 0. And then whatever this is, I don't really care if this is 0 or non-zero, I'm still gonna get a value for z. So factorizing this, we get k minus 2 into k plus 1 not equal to 0. So for this quantity to not be equal to 0, I need k minus 2 not equal to 0, and at the same time k plus 1 not equal to 0. So k can't be 2, and at the same time it can't be minus 1. So any other value other than 2 and minus 1 would guarantee that this system has a unique solution. For part B, for what values of k does the system have no solution? For the system to not have any solutions, we want this to be equal to 0, and this to be some constant that's not 0, or some value that's not 0. Then the system would be inconsistent, because this equation would have no solution. So if this coefficient is 0, then the left-hand side would evaluate to 0. The entire left-hand side is going to evaluate to 0 if this was 0. And then the right-hand side, if it's not 0, then we'd have no solutions. So we want k squared minus k minus 2 to be equal to 0, so that the left-hand side evaluates to 0. And at the same time, we want 1 plus k to not be equal to 0. So we want k equal to 2 or k equal to minus 1. And at the same time, I want k to not be equal to minus 1. So I have to satisfy one of these, but at the same time it can't be minus 1, so I know that the only solution is k equal to 2. So if k is equal to 2, then the system would have no solution. What about infinitely many solutions? For infinitely many solutions, we want this to be 0 and this to be 0. Then it would be 0 equal to 0. So the equation that this row represents would be 0 equal to 0, which is consistent for any value of x, y, and z, or which is true for any value of x, y, and z. So we want k squared minus k minus 2 to be equal to 0, and I want 1 plus k to be equal to 0. So either k is equal to 2 or k is equal to 1. But at the same time, I want to guarantee that k is equal to minus 1. Sorry, either k is equal to 2 or k is equal to minus 1. And at the same time, I want to guarantee that k is equal to minus 1. So overall, the solution is k is equal to minus 1. So overall, if k is equal to 2, we're going to have no solution. If k is equal to minus 1, we're going to have infinitely many solutions. If it's not equal to 2 and not equal to minus 1, then we're going to have a unique solution. For problem 2, let A be a 3 by 3 matrix such that A inverse minus 2i, the inverse of all of that, is equal to this matrix. Find A. So if I find the inverse of this matrix, I would be finding the inverse of this. I would be finding the inverse of this entire thing, so I would be finding A inverse minus 2i. So I would gradually be, so it would kind of simplify the problem if I get rid of this inverse here. So let's do that. To find the inverse of this, I'm gonna go through this process. I think you remember this from class. Okay. So the process is basically just apply row operations to this, to the rows, to the entire row. So for example, if I multiply this row by 2, I'm gonna multiply the entire row by 2. So I would get this. But my aim is to get this side to the reduced row echelon form, which in this case will be the identity matrix. Because I know that the reduced row echelon form of any invertible matrix is the identity matrix. And this matrix is definitely invertible because it's the inverse of some other matrix. So I want to get this to its reduced row echelon form, which in this case is going to be the identity, while applying the row operations on this side as well. So I'm going to apply row operations to the entire row. And then, once this reaches its reduced row echelon form, this will be the inverse of the original matrix. So this will be the inverse of the matrix I started with on the left-hand side. So here, to get it to reduced row echelon form, I'm going to swap the first and third row. So I'm going to get this. So this is the identity matrix, and this is the inverse of the matrix I started with. So A inverse minus 2i is equal to this. Now if I add 2i to both sides, I would get this. A inverse is equal to this plus 2i, which is equal to 2, 0, 1, 0, 3, 0, and 1, 0, 2. And then to find A, the problem asks us to find A. So to find A, I would go through the same process again. So 2, 0, 1, 0, 3, 0, 1, 0, 2, and then with 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So first of all, I want to get this to be 0, so I'm going to multiply this by minus half and add it. So 2, 0, 1, 1, 0, 0, 0, 3, 0, 0, 1, 0, 0, and if I multiply this by minus half, this would be 3 over 2, and then this would be minus half, this would be 0, and this would be 1. Then I'll just multiply this lower row by 2, just to make things a bit cleaner. So 2, 0, 1. So we're multiplying the last row by 2. 1, 0, 0, 0, 3, 0, 0, 1, 0, 0, 0, 3, minus 1, 0, 2. And then now I want to make this entry equal to 0. So I'm going to multiply this by minus 1 over 3 and then add it. So we get 2, 0, 0. And then this is 1 plus 1 over 3, which is 4 over 3. And then this is 0, and then this is minus 2 over 3, then 0, 3, 0, 0, 1, 0, 0, 0, 3, minus 1, 0, 2. Okay, and now I want to make sure that these entries are all ones. So I'm gonna divide the first row by 2. So I get this. And then this row by 3. And then this row by 3. And now, since the left-hand side is now the identity matrix, then I know that the right-hand side is A. So A is equal to 2 over 3, 0, minus 1 over 3, 0, 1 over 3, 0, minus 1 over 3, 0, 2 over 3. And we've solved this problem. For problem 3, consider this matrix. Show that A is not invertible. So to show that A is not invertible, there are a few ways. We can... Something you might notice is that if you add this column to this column, then you get this column. So this would directly show you that it's not invertible. You can also try to calculate its determinant. So these are both ways these are both like valid ways. And you can also try to get it to reduced row echelon form. And if its reduced row echelon form is equal to the identity, then it's invertible. Otherwise, it's not invertible. So the simplest thing to write here is that first column plus second column equal to third column. So A is not invertible. For part B, for a real number A, consider the vector 1, A minus 2, A squared plus A. Find the values of A such that the linear system Ax equal to B with x equal to x1, x2, x3 is consistent. So Ax is equal to B. So we're trying to solve basically these equations. We have x1 plus x2 plus 2x3 equal to 1. We also have minus 2 x1 minus x2 minus 3x3 equal to A minus 2. And then we have x1 plus 2x2 plus 3x3 equal to A squared plus A. So this is the system, and we're asked to find the values of A for which this system is consistent. And consistent means that it has at least one solution. So this is similar to problem 1, but now we want to satisfy any of these two. So anything that doesn't lead us to no solution. Okay. So we're gonna write the augmented matrix, which is 1, 1, 2, minus 2, minus 1, minus 3, 1, 2, 3, and then 1, A minus 2, A squared plus A. And we want to convert it to row echelon form. So 1, 1, 2, 1, and then 0. If we multiply this by 2 and add it, we're gonna get 0, then 1, then 1, and then A. Then I'm just gonna do the 2 steps right now. So if I multiply this by minus 1 and add it to the third row, we get 0, then 1, then 1, then A squared plus A minus 1. Okay. And then I have to get rid of this one here. I want to make it a 0. So I get 1, 1, 2, and 0, 1, 1A, and then 0, 0, 0, A squared minus 1. So this is the row echelon form. And I want this to be consistent. And on the left hand side, I already have 0. So for this to be consistent, I need this to also be 0. So I need A squared minus 1 to be equal to 0. So I need A to be plus or minus 1. Okay? So for a equal to plus or minus 1, the system is consistent. Let a equal to 1 in part B. Find all solutions of the linear system ax equal to b. So for a equal to 1, we want to find all solutions. Okay. So we have this system basically. 1, 1, 2. I'm just gonna start from the row echelon form because we already got there. So 1, 1, 2, 1, 0, 1, 1, 1. We know a is 1 now. And 0, 0, 0, 0. Okay. So what variable is never the pivot? We have x3. So let x3 equal to t. So it's some free variable. Okay. And then based on this equation, I know that x2 plus x3 is equal to 1. So x2 is equal to 1 minus t. And based on this equation, this one right here, I know that x1 plus x2 plus 2x3 is equal to 1. So x1 is equal to 1 minus x2 minus 2x3, which is equal to 1 minus t minus 2t. So overall we get 1 minus 1 plus t minus 2t, which is minus t. So our set of solutions is minus t, and then 1 minus t, and then t, for every t that belongs to the set of real numbers. So these are the solutions when a is equal to 1. Now for problem 4, part A, let B be a 3 by 3 skew symmetric matrix. So B transpose is equal to minus B. Prove that determinant of B is equal to 0. So B transpose is equal to minus B. And we want to prove that the determinant of B is equal to 0. So if two matrices are equal, I know that their determinant is equal. So B transpose, actually let's go with this notation. So the determinant of B transpose is equal to the determinant of minus B. Okay. And let's write this as minus 1 times B just for clarity. And if I want to take this minus 1 outside the determinant, I can't just take it out like this. I can't say this is minus determinant of B. This is wrong. What I have to do is raise the minus 1 to the power of n, where n is like B is an n by n matrix, so n here is 3. So the determinant of B transpose, which is equal to the determinant of B, we know this property that the determinant of B transpose is always equal to the determinant of B. It's equal to minus 1 power 3 times the determinant of B. So the determinant of B is equal to minus determinant of B. So we know that 2 times determinant of B is equal to 0. So determinant of B is equal to 0. For part B, let A be a 2 by 2 matrix such that a squared plus a minus I is equal to 0. Find A inverse and prove that A cannot be skew symmetric. So for these problems, it's a good idea to isolate I. So the plan for such a problem is try to get to a form of A times something equal to I. So we want to leave I on the right hand side and then try to factor out A, and then whatever remains is A inverse, because A times B is equal to I means that B is the inverse of A, right? So applying this to this problem, we have A squared plus A minus I is equal to 0. So we can do A into A plus I is equal to I. So A inverse is equal to A plus I. And that's it. We found A inverse. Now we want to prove that A cannot be skew symmetric. To prove that something cannot be true, it's a good tactic to keep in mind that to try to prove it by contradiction. So that's a good place to start from. So let's assume towards a contradiction. So it's a good idea to be clear about what you're trying to do. So we're assuming towards a contradiction that A is skew symmetric. So it's a good idea to just, since it's a small matrix, so it's a good idea to just think of A as these four values, A, B, C, D. But we know that A is skew symmetric, so these are 0, and these are some value, let's keep calling them B. So this is B, and this is necessarily minus B, right? This is the general form of a 2 by 2 skew symmetric matrix. So here it's important to note that it's a 2 by 2 matrix. So A inverse based on this assumption is equal to 1 over determinant of A. This is the rule for the determinant of a 2 by 2. So it's 1 over determinant of A, and then in general we would do dA minus B minus C, right? But now D and A are 0, and then minus B is minus B, and minus C is B. Okay. So what's the determinant of A in this case? 1 over the determinant of A here is B squared, and then 0 minus B, B 0, which is equal to 0 minus 1 over B, 1 over B, and 0. Okay, but A inverse, which is A inverse, which is A plus I, for whatever A, so A inverse based on our previous findings, whatever A is, assuming it's skew symmetric, then if we add I to it, it would be 1B minus B1, right? So we get this form and this form. And these two forms obviously contradict because 1 is not equal to 0. So according to this form, the first entry in the first row must be 1, but according to this form, the first entry in the first row must be equal to 0. So these two forms contradict. So due to this contradiction, we've proved that this statement, that A is skew symmetric, this statement cannot be true. And this is the contradiction, that one is not equal to 0. Okay, on to part 2, the multiple choice questions. Let A be a 3 by 3 skew symmetric, which means A transpose is equal to minus A skew symmetric matrix. Which one of the following statements is false? A transpose is skew symmetric. So let's see if this is false. So A transpose, we know A transpose is equal to minus A. If we transpose both sides, we get A is equal to minus A. A transpose is equal to minus A all transpose. And this becomes A transpose all transpose is equal to minus A transpose. So technically A transpose is skew symmetric. So this is true, this is not the answer we want. Okay, for part B, A transpose minus A is skew symmetric. So we're saying that A transpose minus A, if I transpose that, then do I get A minus A transpose? And the answer here is yes, because we're allowed to distribute the transpose on the while adding two matrices or subtracting two matrices. So this would be A transpose minus A transpose, which is A minus A transpose. So this is also true, which is not what we're looking for. Part C, A squared minus A is symmetric. So A squared minus A all transpose should be equal to A squared minus A for it to be symmetric. So let's check it. A squared minus A all transpose, we can write it as A squared transpose minus A transpose, which is equal to A transpose squared minus A transpose. And we know A transpose is minus A, so this is minus A squared, which is A squared plus A. So it's not equal to A squared minus A, it's equal to A squared plus A. So it seems that this is false. Let's check the other ones. So A11 equal A22 equal A33 is equal to 0. This is true, yes, because the general form of a 3 by 3 skew symmetric matrix is zeros on the diagonal, and these entries are A11, A22, and A33. Then A transpose A is symmetric. So if I transpose this, I get A transpose times A transpose transpose, because I have to flip these and transpose both. And that would be A transpose, and A transpose transpose is A. So
Option C is the false statement.
Problem 6. The values of K for the system with corresponding augmented matrix to be consistent are. So this is the system, and we're gonna transform it into row echelon form. So we can multiply row 1 by -1 and then add it to row 2. We get this. Then we can multiply row 2 by -1 and add it to row 1, to row 3, sorry. And we would get this. 0, 0, 0, K plus 1. And for this system to be consistent, as we've discussed before, we want K plus 1 to be equal to 0, or K equal to -1. That's option B. A, B, and n by n symmetric matrix. Which one of the following statements is false? So n by n symmetric matrix means that A is equal to A transpose. A transpose is symmetric, obviously, since they're equal. So, and we're looking for the false statement, so this is ruled out. 3A A transpose plus A squared plus 2I is symmetric. So 3A A transpose plus A squared plus 2I. If I transpose this entire thing, does it stay the same? So the transpose, I'm allowed to distribute it. So this would be 3A A transpose all transpose plus A squared transpose plus 2I transpose. This would be equal to 3 A transpose transpose. So the constant is okay to take out when we have a transpose, and then I'm distributing the transpose on these two matrices, so I have to flip them. So I get so I would get A transpose transpose and then A transpose plus A transpose squared. So I'm allowed to flip the 2 and the transpose plus 2 I transpose is just I. This is equal to 3A A transpose plus A squared. So instead of A transpose, I'm substituting A since A is symmetric, plus 2I. So this is true. A is invertible. So an n by n symmetric matrix, is it necessarily invertible? That doesn't necessarily have to be the case. For example, this is a 2 by 2 symmetric matrix, and it's not invertible. Let's just check part D to make sure. A minus A transpose is symmetric. So A minus A transpose, if I transpose this, I get A transpose minus A transpose transpose. So A transpose minus A. So yes, this is true.
Because A transpose minus A is equal to A minus A transpose, because A is equal to A transpose.
So part C is the one option C is the one we're looking for. Part 8, let A be a square matrix such that A cubed is equal to A, then A is not invertible. Determinant of A is equal to plus or minus 1. If A is invertible, then A inverse is equal to A, and A power 7 is equal to A squared. Okay. The one with the determinant seems to be the easiest one to deal with, like right off the bat. We can just take the determinant on both sides. So determinant of A cubed equal to determinant of A. Because if two matrices are equal, of course their determinants are going to be equal. And then we have determinant of A. I can take the cube outside when dealing with determinants, equal to determinant of A. Then if I take this to this side and factor out, I get determinant of A into determinant of A squared minus 1 is equal to 0. So determinant of A is equal to 0, or determinant of A is equal to 1, or determinant of A is equal to -1. So this doesn't seem to be necessarily true, unless there's some other condition that that would not allow us to have the determinant of A be 0. So B doesn't seem to be true. Let's check A. A is not invertible. So is it necessary that A is not invertible? It doesn't seem that we can prove this. We could try to provide a counterexample to disprove it, but that could take some time. So let's try to find something that we can actually prove. So A power 7 is equal to A squared. Let's try to do this. So A power 7 is equal to A cubed times A cubed, right? Times A, which is equal to A times A times A, which is equal to A cubed, which is equal to A. So I'm just repeatedly just using this, but I didn't get A squared. So D also doesn't seem to be true. Let's try to prove C. If A is invertible, then A inverse is equal to A. So I have A cubed equal to A. If I multiply by A inverse on both sides, from the right, I get A squared is equal to I. Then multiply by A inverse again, I get A is equal to A inverse. So this one is true. For part 9, let A be a matrix of this form. Which one of the following statements is true? If A equal B equals 0, then A is not in row echelon form. So if this is 0, 0, 0, is this matrix in row echelon form? So the rows that are all zeros are at the bottom. And no, it does seem to be in row echelon form, so this is not true. If A is equal to 1 and B is equal to 0, so this is 0, this is 1, then A is in reduced row echelon form. No, because we have these elements here. So, and also this 2. So this is not reduced row echelon form. If B is not 0, then A is not in row echelon form. So if B is some value, yeah, this would be true. Because if B is not 0, then no matter what the value of A is, the fact that B is not 0, it rules out the possibility of A being in row echelon form. For part D, if A is equal to 0 and B is equal to 1, then A is in row echelon form. This is not true. So C is the correct answer. Let A be a 3 by 3 matrix such that determinant of A is equal to 2. Which one of the following statements is true? Determinant of A minus 2i is equal to 0. This doesn't seem to be necessarily true. Determinant of 2A transpose equal to determinant of A power 4. So the determinant of 2A transpose is equal, if I want to take this 2 out, I would have to raise it to the power of 3. Determinant of A transpose, which is equal to 8, times determinant of A transpose, which is determinant of A, which is equal to 16. And determinant of A power 4 is equal to determinant of A raised all to the power of 4, which is 2 to the power of 4, which is 16. So this is true. Now let's just go over the other options. A transpose A is not invertible. This is not true, because the determinant of A transpose A, I'm allowed to split the determinant when I have multiplication. So it's determinant of A times determinant of A transpose. And A transpose has the same determinant as A, so this is 2 times 2, which is 4. So this is not true. Determinant of 2A is equal to determinant of A squared. Determinant of 2A is going to be 2 squared times 2 cubed times 2, which is 16. And determinant of A squared is going to be 2 squared, which is 4. So this is also not true. So option B is the correct one. For part 11, let A be an n by n matrix. Which one of the following statements is false? If ax equal to 0 has only the trivial solution, then a squared x equal to 0 has only the trivial solution. If ax equal to 0 has the trivial solution, then a is invertible. So the determinant of a is not equal to 0. Then the determinant of a squared is definitely not equal to 0. So this is true. So this is not the option we're looking for. Oh, sorry. This is not the option we're looking for. For part B, for option B actually, if A is not equal to 0, then the matrix equation AX equal to B has a unique solution for all B. This is not necessarily true, because what if A is not equal to 0, but A is not invertible? Then this wouldn't have a unique solution for all B. So this is a false statement. If AX equal to B has infinitely many solutions for some B, then A is not invertible. This is true. These are just things that we have to know. If determinant of A is not 0, then the reduced row echelon form of A is I. This is true. Determinant of A is not 0, so A is invertible. And reduced row echelon form of A is I also means that A is invertible. So option D is true. Let V1 equal 1, 2, 1, V2 equal 1, 1, 0, V3 equal 3, 5, 2. Which one of the following statements is false? If V3 minus V2 equal to CV1, then C equal to 2. So let's just try this. We have V3 minus V2. This gives us 2, 4, 2. And this is indeed equal to 2V1, since V1 is 1, 2, 1. Okay, part B, or actually option B, 2V3 minus 4V1 equal to 2V2. So 2V3 minus 4V1, it's equal to 6 minus 4, 10 minus 8, 4 minus 4, which is equal to 2, 2, 0, which is indeed equal to 2V2. And then for option C, the only values of C, D such that CV1 plus DV2 equal to V3 are C equal to 2 and D equal to 1. So we have CV1, which is C, and then 1, 2, 1, plus D, 1, 1, 0, equal to V3, which is 3, 5, 2. So the system we have is C plus D equal to 3, and we have 2C plus D equal to 5, and we have C equal to 2, and we can try to solve this system. We can actually write it in an augmented matrix form and then get the reduced echelon form, etc. And eventually we're gonna reach the conclusion that yes, this system is consistent and it has a unique solution, and that unique solution is C equal to 2 and D equal to 1. We can actually just see this pretty quickly. So if we substitute C here, we get D equal to 1, and if we substitute C equal to 2 here and D equal to 1, we get 5 equal to 5. So the system is consistent, and C equal to 2 and D equal to 1 are is the solution. C equal to D equal to 1. And there exists a real number C such that V3 minus CV2 equal to 0. So we're basically saying 352 minus C V2 is equal to 0. So 3 minus C, 5 minus C, 2 equal to 0. This is saying that 2 is equal to 0, which isn't true, so D is the false one. For part 3, this is a true or false question. If A and B are symmetric n by n matrices, then AB is symmetric. This is not necessarily true. Yeah, I don't see a reason why this is true. I think we can find a counter example. For example, if we have this. Okay, so dot the first row with the first column, we get 1. The first row with the second column, we get 2. The second row with the first column, we get 3. The second row with the second column, we get 3. So this is not symmetric, even though these two matrices we started with are symmetric. So this is false. We proved this by finding a counterexample. If A and B are square n by n matrices such that B is not invertible, then AB is not invertible. This is true. We just know this as a fact. The product of two matrices where one of them is not invertible, the product is not going to be invertible. And to prove this, we can say that the determinant of AB is equal to the determinant of A times the determinant of B. which is equal to the determinant of A times 0, since B is not invertible, which is 0. So the determinant of AB is 0, which makes it not invertible. If A is a non-invertible 3 by 3 matrix, then the system AX equal to B is inconsistent. This is also false actually, because it could be consistent for some values of B. So it's not necessarily true. Even if A is non-invertible, the system can still be consistent for some values of B. Every triangular 3 by 3 matrix is invertible. Every triangular 3 by 3 matrix is invertible. No, this isn't necessarily true as well. For example, this is a triangular, this is a triangular 3 by 3 matrix. Oh, it's actually not clean at all, but this is an example. So the determinant of this is 0, so it's not invertible. If A and B are n by n matrices such that A is invertible and A inverse B transpose is invertible, then B is invertible. So this is invertible. So I know that the determinant of this is not equal to 0. If I want to decompose this a bit, I get this times B transpose is not equal to 0. So the determinant of A inverse times the determinant of B transpose is not equal to 0. The determinant of A inverse is 1 over the determinant of A. And then I have B transpose not equal to 0. And so this can't be equal to 0, because if B transpose was equal to 0, then we'd get a contradiction with this. And so the only way for this, for us to not contradict with this, would be for the determinant of B transpose to not be equal to 0, and obviously the determinant of B transpose is the same as the determinant of B. So this is true. If A is a 3 by 3 matrix such that determinant of 2A inverse equal to 4, then determinant of A transpose is equal to 2. So determinant of 2A inverse is equal to 2 power 3 times 1 over determinant of A, which is equal to 4. So determinant of A is equal to 2, which makes the determinant of A transpose equal to 2 as well, since the determinant of A is equal to the determinant of A transpose. And note again that when I take the 2 out here, I have to raise it to the power of 3. So this is true as well. This brings us to the end of this session. Hopefully you found this beneficial. Hopefully this answered some questions you had. Reach out with any questions if you still have some. And yeah, I hope you do well on your quiz.